Hey everybody, welcome to the shop. I'm Jarrell with Jarrell Education. Today, we're covering a video on when something falls and there's a resistive air force. Now in this case, we're going to be covering it when it's proportional to the velocity. We're going to find terminal velocity, and we're also going to find an expression for the velocity at any given time. My next video is going to cover one where the resistive air force is proportional to the square of velocity, all right? But right now, let's go into this one. It's enough to fill a video. So let's get started and pause the video as you go through, you know what I mean, and try to solve the steps. But don't forget, look at the previous two videos before you attempt to do this one, okay? Because there's a lot of stuff that I explain to make it a little bit easier, all right? So as is always the case, if this video helps you and you like it, please like and subscribe to the channel. Leave any comments below for any things that you want to see, all right? All right, let's go. Okay, today I want to go through the final problem in this air resistance that we're going to cover. All right, now what we said is this: the mass shown at the right is allowed to fall for a long period of time. The air resistance the mass experiences is proportional to the velocity of the mass as it falls. Okay, so one particular type of problem that you're going to come up against is this one, where as the thing falls, so essentially we have this, right? We have the mass, all right, and you drop it. So at time zero, the only force acting on it is the gravitational force, so that would be mg down. Then as some time passes and this thing falls, you're going to get, as it starts to pick up speed, the wind resistance underneath it is going to start to accumulate, and that's going to create a force in the opposite direction. So that's not, I don't want to say it's going to stop it from speeding up as much, is how you should think of it. And then as it speeds up a little bit more, just not as fast as it did a moment ago, this resistive force is going to get bigger and bigger. Now, eventually what's going to happen is the thing is going to fall so fast that the air resistance force is actually going to be the same length as the mg vector. Okay, so what that means is what it doesn't mean is that the object stops falling. What it means is it continues to fall, but it doesn't speed up anymore. So at that point, it'd be moving at a constant velocity. It wouldn't be accelerating anymore. So the model that we've chosen to cover today, and again, if you haven't seen the previous two videos on this, watch those first, because I sort of walk you through all the basics of it, and it makes a lot of the things I'm going to do here a little bit easier. Okay, so what we're going to cover now is what happens when that wind resistance force is proportional to the velocity. Now, it doesn't have to be that. It could be proportional to the square of the velocity. We could take in the properties of, we might have to take in the properties of the shape of the object or the fluid that it's moving through. But in this case, we're just keeping it as simple. And you'll see it's not that simple, but basically what's going to happen in this case is the resistive force is proportional to the velocity. So here we go. First part, find the terminal velocity of the mass. Well, that means this is BV, right? Where B is just some constant. I don't know what it is. It might be 7 or something like that. So we can say this: the summation of all the forces is equal to ma. Now we're only moving in the vertical direction, so the forces are going to be, we're going to say mg minus bv is equal to ma. But if we've reached terminal velocity, that means a is 0. It's not accelerating anymore. So what I would have then is mg minus b, and now we'll call it v sub t because we're setting this equal to 0, and that would be the terminal velocity. Now if I add bv sub t to both sides, plus b sub t and plus bv sub t, I end up getting on the right b v sub t, and on the left that's just equal to mg. So let's go up here and we'll finish solving that. I end up with v sub t is equal to mg divided by b when I divide both sides by b. And that would be an expression for what the terminal velocity would be when the thing stops speeding up. Now, if I look at part B, I want to sketch what I think that graph is going to look like. So if this is the velocity and this is time, well, initially if I dropped it, the initial velocity would be 0. And I know that this is v sub t, whatever that number turns out to be, okay? And then I would expect that first, when the resistive force wasn't that high because it hasn't started moving that fast yet, it would accelerate like you would normally think. So it would look kind of linear, but then as time went on and it caught up, the velocity would slow down. It would start to approach that terminal velocity. Okay, and now for part C, we're actually going to go through and do some calculus on this. So I want to point out the first two parts, really no calculus involved. You just really have to understand what's going on there. Okay, now we're going to use calculus to solve it. Okay, so let's maybe scroll up a little bit and go back to this. Summation of all the forces was equal to MA. Okay, now what we had was this. We had mg minus bv was equal to MA. Now you might be asking me, all right, why did you let mg be positive since it's down? The way we're handling this is whichever way the acceleration is occurring, okay, at least initially in this case, that's going to be the positive direction. So I'm choosing the downward direction to be positive. Now the other insight you need for solving this, right, is to say mg minus bv is equal to m times dv dt. We're making a note that the acceleration is actually the derivative of velocity. So now what I've done is now I have an equation, okay? And now my equation doesn't have two separate variables in it. It's basically got a v and a rate of change of v. So they're related to each other through time. And remember what we're trying to do? We're trying to find the function v of t. That's what we're actually looking for, okay? So let's continue. Okay, so now I'm going to rewrite this. Oops, let me switch back to the pen. I'm going to rewrite this down below. So I have m dv dt is equal to mg minus bv. So now what I'm going to do is I'm going to separate out. I'm going to get the dv's and the v's on the left and everything else on the right. So the first thing I'm going to do is multiply both sides by dt. So now I have this. I have m dv is equal to mg minus bv all times dt. And I guess I should put that in parentheses. Okay. And now I'm going to divide both sides by mg minus bv. mg minus bv. So it cancels out over there. And now I have m dv over mg minus bv is equal to, I just got a lonely old dt over there. Okay, so the first thing I'm going to do now, I'm going to start cleaning this up a little bit. I'm going to get rid of this m by dividing both sides by m. So I'm going to multiply over here by 1 over m, so that'll cancel out, and then 1 over m there. And now what I have, let me scroll up a little bit, is I have 1 over mg minus bv dv is equal to 1 over m dt. Okay, now let's move over to here. Okay, draw a line so we separate it a little bit. Now what I'm going to do here is I'm going to take this, right? And again, this is the point I would say go back and watch the first two videos because I show you how to handle this and just make things a little bit cleaner. I'm going to factor out a negative b. All right, so what I have now is this 1 over on the left. Okay, I've got negative b times. Now on the inside, I'm going to have this. I'm going to have mg over b negative plus v, and then dv. And then that's equal to 1 over m dt. Okay? And you can check if I multiply the b back in, if I distribute it back in, I will end up with exactly the expression that I had over there. Okay? So now I'm going to multiply both sides by negative b. So I end up with this now. 1 over v minus the constant mg over b dv is equal to, now that I've multiplied both sides by b, negative b over m dt. So what I did there is I multiplied this side by negative b and then this side by negative b. Now pause the video, make sure that you're okay with that. Leave me a comment if you're not, and I'll try to explain that better. But let's keep on going. Now what I'm going to do is integrate the left and integrate the right. Now, this becomes the natural log of the absolute value of v minus mg over b. And that's equal to, when I integrate this with respect to t, negative b over m times t plus a constant. Okay, now the way I solve this for v, right, the way I get v out of there, is I basically make the left and the right an exponent on e. So I have e raised to the both sides as a power. Now let's scroll up a little bit, try to leave that in the window. So now I have this. I have v minus mg over b is equal to e to the negative b over m t plus c as an exponent. And now, like we said before, I'll scroll up a little bit now. This can become v minus mg over b is equal to a times, for some constant a, e to the negative b over m times t. Now, if you forgot how to do this, this is explained in one of the previous videos, but you have to remember that when I have e to the negative b over mt plus c, that's the same thing as e to the negative b over mt times e to the c. And then e to the c is just another constant, which I'm just calling a. Okay? So now, let's keep going. V is equal to, I'm going to add mg over b to both sides. A e to the negative b over mt plus mg over b. And there it is. There's my velocity function for t in general, but the only problem is I just don't know what that a is. So I'm going to figure that out now with my initial condition. Do you remember what it was? Think about the problem. So in this case, the initial condition would be that I dropped it. So that means initially, at time 0, the velocity was 0 when I let it go. So I'm going to use that right now. I'm going to say, well, when t was equal to 0, v was equal to 0. Just as is appropriate for this problem. So now what happens is for t, I put in a 0. That means the exponent becomes 0. That means e to the 0 is just 1. And for v, I'm also going to put in a 0. So I end up with 0 is equal to a times 1 plus mg over b. And if I solve that for a, I just subtract mg over b off both sides. Remember, mg over b is just a constant. And I end up getting, let me scroll up a little bit, I end up getting negative mg over b is equal to a. Now let me make a little box here, and we'll put our stuff over here. So now, I'm going to take this constant, and I'm going to substitute it back in for what I know a to be now. So v is equal to negative mg over b e to the negative b over mt plus mg over b. And I can simplify it a little bit by factoring out the mg over b constant. So I'd have this. V is equal to, when I factor this out and this out, I can write that as mg over b times 1 minus e to the negative b over mt. Okay? Now a couple things to point out, right? I said in the problem it falls for a long time. That means it has enough time to reach terminal velocity. And if you let t be like a large number of seconds, right? You let this fall for a while. That means this exponent is going to become a very big negative number. And then e to a very big negative number is a very small number close to 0. So this whole thing, as time goes on, approaches just 1. And you end up getting v, the terminal velocity, as it should be when it falls for a long time.